In our last video, we have seen about the various types of algorithm. Here, how can we evaluate that various types of algorithm? Evaluating scheduling algorithms involves analyzing their performance under various scenarios and workloads, benchmarking, simulations, analysis, and these things are used to evaluate that particular algorithm. Benchmark tests measure algorithm performance using standardized workloads and metrics such as throughput, response time, and CPU utilization. Simulation models emulate real world scenarios to assess algorithm behavior, predict system performance, and identify potential bottlenecks or inefficiencies. Analytical methods use mathematical models and algorithms to analyze the efficiency, fairness, scalability, and trade offs of different scheduling algorithms, aiding in algorithm selection and optimization. Process synchronization. The critical section problem. The critical section problem addresses challenges in concurrent access to shared resources, aiming to ensure mutual exclusion, progress, and fairness among processes. Mutual exclusion. Mutual exclusion in the sense ensures that only one process accesses a shared resource at a time, preventing data corruption and race conditions. Progress guarantees that processes waiting to enter critical sections eventually get access, avoiding deadlock and live lock situations. Bounded waiting ensures that a process waiting to enter a critical section does not wait indefinitely, preventing starvation and ensuring fairness. And synchronization hardware. Hardware mechanisms provide the foundation for implementing process synchronization and mutual exclusion. Locks such as mutexes, binary semaphores provide exclusive access to shared resources. Processors acquire lock before entering critical sections and release them afterward to allow other processes access. Atomic operations ensure that a sequence of operations executes as a single indivisible unit, preventing interruptions or interference from other processes. Synchronization primitives like test and set, compare and swap, and barriers offer low-level synchronization mechanisms for coordinating access to shared resources and managing concurrent execution. Semaphores are high-level synchronization constructs used to manage access to shared resources and coordinate process execution. Binary semaphores allow only one process at a time to access a resource, ensuring mutual exclusion and preventing race conditions. Counting semaphores manage a limited number of resources instances, allowing multiple processes to access resources concurrently up to a specified limit. Classical problems of synchronization. Classical synchronization problems highlight common challenges in coordinating access to shared resources among concurrent processes. Producer-consumer problem involves producers generating data and consumers consuming data from a shared buffer, requiring synchronization to prevent buffer overflows or underflows. Readers-writers problem deals with multiple readers and writers accessing shared data, balancing read access concurrent and write access exclusive while ensuring data consistency. Dining philosophers problem illustrate resource allocation and deadlock avoidance in a scenario where philosophers alternate between eating and thinking, requiring synchronization to prevent deadlock. System model. Deadlocks occur when processes hold resources and wait indefinitely for additional resources held by another processes, leading to system-wide resource unavailability. Processes. The system model includes processes that compete for resources and may enter deadlock states if resource requests are not managed properly. Resources such as CPU time, memory, I/O devices are essential for process execution and can become deadlocked when processes hold them exclusively. Allocation matrices. Allocation matrices trace resource allocations to processes, highlighting potential conflicts and dependencies. Wait for graphs. Wait for graphs visualize resource allocation and process dependencies, identifying circular wait conditions that lead to deadlock. Thank you.